Let's begin our topic. This is RA01, Foundations, the ordered field R, and Completeness. First, we describe the field axioms in words. Addition and multiplication on the real numbers are both commutative, which means the order you combine two numbers does not matter. They are both associative, which means when you combine three numbers, the way you group them does not matter. There is an additive identity, 0, and a multiplicative identity, 1. Every number has an additive inverse, so for any number there is a negative version that cancels it to 0. Every non-zero number has a multiplicative inverse, so it can be divided into 1. Multiplication also distributes over addition. Next, we describe the order axioms in words. For any two real numbers, exactly one of three things is true. Either the first is less than the second, or they are equal, or the first is greater than the second. The order is transitive, so if one number is less than a second, and that second is less than a third, then the first is less than the third. The order is also compatible with addition and multiplication, so adding the same number to both sides preserves the order, and multiplying both sides by a positive number preserves the order too. Putting this together, we say that the real numbers with addition and multiplication form an ordered field. Now we add one more property that makes the real numbers special. This is called the completeness axiom. In words, it says that every non-empty set of real numbers that is bounded above must have a least upper bound, and that least upper bound is itself a real number. Here is the key example that shows the rational numbers do not have this property. Consider the set of all rational numbers whose square is less than 2. This set is bounded above by 2, since every number in the set, when squared, gives something less than 2, so no element of the set can be larger than 2. However, this set has no least upper bound within the rational numbers. The natural candidate for the least upper bound would be the square root of 2, but the square root of 2 is not a rational number, so it cannot serve as the least upper bound inside the rationals. As a check, we ask, could some other rational number be the least upper bound instead? For any rational number we try that is close to the square root of 2, we can always find another rational number in the set that is even closer, so no rational number ever works as the true boundary. This confirms that the rational numbers fail completeness. Now let us unpack the definition of supremum in words, since this is the idea behind the least upper bound. We say that M is the least upper bound or supremum of a set if two conditions hold. The first condition is that every element of the set is less than or equal to M. This means M really is an upper bound, nothing in the set goes above it. The second condition is that M is the smallest such upper bound. In words, for every small positive gap, which we call epsilon, there exists some element of the set that is bigger than M minus epsilon. This means you cannot shrink M down even slightly and still have an upper bound, because the set always has elements creeping up arbitrarily close to M. As a final check, apply this definition to our earlier example. The real number, square root of 2, satisfies both conditions for the set of rationals whose square is less than 2. Every element of that set is at most the square root of 2, and rational numbers in the set get arbitrarily close to it. This confirms that the square root of 2 is the least upper bound in the real numbers, even though it was missing from the rationals. This is exactly why completeness is the property that separates the real numbers from the rationals.